Hello everybody, and welcome back to another video. Today we're going to be proving Euler's identity. So e to the xi is just cos x plus I sine x. So yeah, this should hopefully be fun. And also it's going to be one of the tamer videos, so don't expect any crazy integration or like Laplace transforms. So hopefully people in the BC class at TA4 can understand it. But that aside, this will nevertheless be fun. So let's get started, shall we? The Taylor series for e to the x, as you might recall, is just the sum from k equals 0 to infinity of x to the k over k factorial. So to get from this to this using series expansion, all we really need to do is add an I here and add an I here where the I is also being raised to the k power. And the thing that makes this extremely interesting is that we have this I to the k term here. So to kind of dissect this a bit, let's actually make a table out of it real quick. So we're gonna have our k here, and then our I to the k here, and we're gonna have 0, of course, and then 1, 2, 3, and then 4. So I to the 0 is just going to be, well, 1 by definition, because anything to 0 power is really just 1. I to the first power, again, just 1. Multiply that by I, we're going to end up getting -1, because I squared is -1, again, by definition. Multiply that by I, we're going to get -I. Multiply that by I again. This is getting quite redundant, but we're done now, thankfully. We're back to 1. So you'll see that this cycle really just repeats. So the next one, we're going to get I, and then so on and so forth. So a couple of things that I would like to point out with this, and this is going to kind of form our motivation for what we're going to do next, is that look at our even components here. So even, it's just alternating from 1 and then to -1, 1 and then eventually back to -1. So it's almost like a -1 to the some power, some integer power term. But if you also look at our odd components right here, it's the same thing, but just with an I in front. So it's we go from I to -I, and then we're gonna go back to I and then -I, and so on and so forth. And this is really the basis for what we're going to do next, which is going to be to split up the sum into a sum over all even numbers. So for k even, plus the sum of this right here for all odd k. And the reason for that is really just to break this up into its real, its even components, and its odd, its imaginary components. So yeah, let's actually just go ahead and do that real quick. So our sum over our even components, this is just going to be our sum over, I'm just going to call it k even for now, of I to the k, x to the k, over k factorial. Another way we can actually express k being even is just, instead of writing just a normal k here, is that we express it as 2k. And the reason for this is that here we're summing over like every other integer in a way. Whereas if we express it as here, we can just sum over every single integer because the k is being multiplied by 2. So if we express k as now 2k, we have the sum, but instead of writing k even, we're going to have like a proper sum over k equals 0 to infinity of I to the 2k times x to the 2k over 2k factorial. Now, to simplify this just a tad bit, we're just going to express I to the 2k by properties of exponents as I squared to the k, but we know what I squared is. I squared is just -1, so we end up getting the sum over all k, well, all positive k and 0, I guess, but that's not the point. -1 to the k times x to the 2k divided by 2k factorial. And you'll see this actually does reflect a lot our table right here. So we have our -1 to the k term for our even, and then here you will also see, sorry, can also see this. So it's alternating back and forth. So 1, -1, 1. And let's do our odd ones now. So it's gonna start off the same in a way. So we're gonna have k odd over, and there's something over k odd. We have an I to the k times x to the k over 2. Oh, sorry, spoiler there. K factorial. So instead of expressing just as a sum over odd k, we can sum over every k if we just take our k and make this instead a 2k, but then plus 1. So it's very similar to what we did for our even one right here. So if we take an integer, multiply it by 2, we're always going to get something even. But if you then add 1 to that, you're always going to get something odd. So this is just another way to express a sum over odd integers. So to do that, or applying this really, we have our sum from k equals 0 to infinity of I to the 2k plus 1 times x to the 2k plus 1 over 2k plus 1 factorial. And again, we're just going to simplify the I to the 2k plus 1 term. So we're going to have an I to the 2k plus 1. And by properties of exponents, this right here, well, we can just bring this -1 down and make that an I. So we're going to have an I times our I to the 2k. But we already figured that out. That's just I times -1 to the k. Meaning that we can express this right here as our sum from k equals 0 to infinity of an I out front, but then we're going to have our -1 to the k times x to the 2k plus 1 over 2k plus 1 factorial. And two things actually that you might notice here is that, again, this reflects the behavior we saw in the table. So for our odd k in our table, you'll remember that we got I and then -I and then repeat. And this is what we see here. We just have an I times a -1 to the k. So what we did earlier, based off what we did earlier, our answer, what we want, e to the xi, to be, is just going to be the sum of all of our even terms plus all of our odd terms. So all you have to do is add these series together. But before we do that, you'll notice that this right here, this is just the series for cosine. This is just by definition the same thing as just the cosine of some x. And you'll notice here that this is very similar to sine, save this I, but by properties of sums we can just kind of stick this on the outside. So this is the same thing as I times the sine of x. Meaning that if e to the xi is just the sum of these two things, then what we're left with is e to the xi is just the cos of x plus I sine of x, which is exactly what Euler's identity is. So yes, I hope you all enjoyed this video, and I'll see you all in the next one. Adios.